So good evening, everyone, and welcome back to a new year with Sliver, discussing research and design as an interconnected affair, its modalities, and how both research and design, or as an interconnected affair, contribute to the evolution of the discipline of architecture and, of course, its pedagogy. Today, we have the great pleasure to host Professor Jenny Sabin, an architectural designer whose work investigates the intersections of architecture and science and applies insights and theories from biology and mathematics to the design of material structures. Jenny Sabin is the Arthur and Isabel Wiesenberger Professor in Architecture and Associate Dean of Design at Cornell College of Architecture, Art and Planning, where she established a new advanced research degree in Matter Design and Computation. She's also the principal of Jenny Sabin Studio, an experimental architectural design studio based in Ithaca, and director of the Sabin Lab at Cornell. In 2006, she also co-founded the Sabin+Jones LabStudio, which is a hybrid research and design unit together with the biologist Peter Lloyd Jones. And in 2017, they published a great book called LabStudio: Design Research Between Architecture and Biology. So she was also awarded a Pew Fellowship in the arts in 2010 and was named the US Knight Fellow in Architecture. And in 2014, she was awarded the prestigious Architecture League Prize for Young Architects and was announced as a woman in by Architecture Records National Woman in Architecture Award, selected as Innovator and Design in 2006. So she has exhibited nationally and internationally, and some of you might have seen her work in the 9th ArchiLab Naturalizing Architecture at FRAC exhibition in Orléans in France. And most recently, she is also part of the exhibition Beauty at the 5th Cooper Hewitt Design Triennial. But most of you, or maybe that's where I accounted her work in a little bit more depth, was when she won the Young Architects program in 2017 with her submission Lumen at PS1 in New York. Jenny Sabin also participated in a conversation with our student body for the platform called Abstract, which was initiated by Studio Hani Rashid and launched last year via Instagram and in print. So in a way, we are really happy to have her back. So she's no stranger to the Angewandte, and we are happy to have her back. And today, after the lecture, she will be in conversation with Professor Wolf Mangelsdorf, who is our chair for structural design, as well as partner of Bureau Happold in New York City and the global head of design, technology, and innovation. So looking forward to an exciting contribution on research and design, which operates really across disciplines. I would like to give a warm welcome and hand the screen over to Professor Jenny Sabin.
Thank you so much, Maya, for the generous introduction. It's really a sincere pleasure to be with all of you this afternoon, this evening, wherever you might be in the world. It's an honor to take part in the Sliver lecture series. So thanks again so much for the invitation. So I will go ahead and share my screen. Does everything look okay on your end?
Yes, it does.
Great, perfect. So the title of my lecture is Transdisciplinary Architecture, Biosynthesis, and New Paradigms of Making. I'm going to start the introduction to my talk with a familiar and unfortunately now well-known fact that according to the World Green Building Council, building and construction account for 40%, it's a huge percentage, of annual global carbon emissions, which are significantly contributing to global climate change, and imagery such as what you see here that now unfortunately is becoming increasingly more familiar to all of us. The heating, lighting, and cooling of buildings accounts for 28% of this total, and the remaining 12% comes from what is known as embodied emissions or upfront carbon, associated with materials, construction, and building processes throughout the building life cycle, including concrete waste, as we can see in the lower left-hand side. The energy intensity per square meter of the global building sector must improve on average by 30% by 2030 to meet international climate ambitions as set in the Paris Agreement. At the same time, the COVID-19 crisis is forcing a reconsideration of our workspaces, residences, and other occupied structures, such as the studio spaces that many of us teach, work, and learn in, as well as products and supply chains, as these crises reveal systemic issues of diversity, equity, and inclusion that have inspired new models for distributed practice and fabrication, such as Operation PPE, which leveraged the participatory and networked space of design and making across disciplines to innovate design solutions to rapidly respond to gaps in supply chains at times of extreme crisis, to importantly make impact and save lives. How do we address these crises? Radical new models are needed for both design research, alternative forms of practice, architectural pedagogy, and collaboration across disciplines, industries, and practice. One approach entails the hybridization of labs and studios to fuse innovations across science and design to generate next-generation building materials and structures that are adaptive, efficient, smart, and resilient. This lecture describes topical areas of research and practice that feature projects emanating from my lab at Cornell University and my practice based in Ithaca, New York, that integrate bio-inspired design processes and the dynamics of light and energy to innovate responsive, non-standard building skins, biobricks and tiles, and sentient spaces that are not only performative, but generate what Jenny Odell calls attention-holding architecture. We ask, how might buildings behave more like organisms, responding to and adapting to their built environments? We integrate the premise that nature is resilient, not efficient, into our thinking and processes analogically. We embrace transdisciplinary design with a focus on problem and knowledge generation over problem solving through collaborative design processes that are emergent, transforming, and evolving for innovative applications across disciplines and disciplinary frameworks. With strong links to my lab, which is based at Cornell and the College of Architecture, Art, and Planning, the driving mission behind my practice and research is to create resilient, science-driven, and transformative spaces with and for diverse communities and publics. As my friend and colleague Achim Menges recently stated in conversation with my students, we need more research in practice and more practice in research. We frequently start with very simple parts and rules that through feedback and iteration produce much more complex spatial wholes. This interest probes the productive tinkering and misuse of digital fabrication machines frequently found in alternate industries such as textiles, medicine, and the automotive industry. Importantly, these issues are informed by craft and making to produce bio-inspired material systems and software design tools that hopefully have the capacity to facilitate embedded expressions in our built environment. A seminal reference for my work is the biological extracellular matrix, which is a dynamic protein network that physically and chemically couples the exterior environment of cells with their interior and vice versa. And these are some of the key features of the extracellular matrix, which was introduced to me by my longtime collaborator and friend, Dr. Peter Lloyd Jones, in the context of the Sabin+Jones LabStudio. I've also had the pleasure of working with material scientists such as Xu Yang, who engages in biomimicry in the true definition of the word, to develop entirely new materials that are super hydrophobic, super hydrophilic. She looks at the feet of gecko and the leaves of lotus plants, and also the wings of butterflies to explore topics such as structural color, which is something that I'll come back to in a moment. To look at the possibilities of designing more dynamically with human perception and also, importantly, the dynamics of energy and light. More recently, I've been collaborating with Dr. Dan Lau, who's in biological and environmental engineering at Cornell, to develop programmable materials through the integration of DNA sequencing, so limiting the amount of energy input and really thinking about how the characteristics and the design of materials can respond dynamically to their local environments. In discerning which effects and materials are actually scalable, my practice and research operates across three distinct phases. The first includes the development of new tools and novel methodologies to model behavior. This might be based on a particular data set coming forth from biology or a particular material or media. The second entails architectural prototyping, so starting to productively contaminate the process of making with the constraints of fabrication and materials and so on. And this is where we integrate 3D printing, digital fabrication, and really begin to grapple with scale. Not all of these systems are scalable in terms of application. And then finally, engaging ecological building design and the built environment. So moving forward the successful prototypes and into the realm of architecture. So it's a purposefully slow process to ensure that we are rigorous and also, importantly, are responsible with how we negotiate scale. We couple architectural designers with engineers and scientists in a research-based laboratory studio to develop new ways of thinking, seeing, and working in each of our fields. These transdisciplinary collaborations are working to develop adaptive materials that are not just elements and things and buildings, but hopefully will generate immersive spaces, both acting upon and responding to both inhabitants and the dynamic conditions of the built environment. So like the cells in our own human bodies, sensors and materials in the not so distant future will learn and adapt, making buildings not only smart, but also healthy, aware, and sensate. I have three topics that I'm going to go through this evening that relate to these primary topics that I just unfolded in my introduction, and importantly, address some of these key questions and crises, starting with adaptive materials and really addressing the question that I just posed, and importantly, connecting that to how we might begin to think about personalizing architecture in our own engagements. I won't talk about the eSkin project in detail, but this was an important project both for the research but also in terms of our work on the topic of structural color and designing dynamically with light and energy, and importantly, thinking about how that engages human perception. On the research side, and importantly, the highly experimental and kind of radical approach that we explored through LabStudio, which was founded in 2005 while I was teaching in the graduate Department of Architecture within the School of Design at the University of Pennsylvania. And at that time, I was working with Peter Lloyd Jones, who I just mentioned, who introduced me to the ECM, along with colleagues in material science, including Xu Yang. And we think at the time we were the first model of a truly collaborative transdisciplinary design research space shared between architects and biologists. And so we decided to go after a fairly sizable grant administered by the National Science Foundation, which is one of the largest federal funding agencies in engineering and the design arts in the States. And they were interested in teams that would approach the topic of sustainability through a radical model. And specifically, they were interested in approaching the issue of building heat gain in high-rise buildings. So we had a few years under our belts of collaborating in the context of LabStudio, framing a way of working together, figuring out how to communicate effectively, and learning from the program director at the NSF. This was a key component to our success in acquiring one of 10 multi-million-dollar grants. So this not only put an institutional stamp on what was seen as a highly experimental and radical model, but it also allowed us to really push forward with the necessary resources with the research. So specifically what we proposed was the development of a thin film technology that could be integrated within either existing facade design and construction or a new facade design. We developed a whole series of prototypes exploring specifically structural color and how we could harness that across scales. So this prototype actually took us 2 years to develop. I won't go into detail on this, but if you're interested in taking a deep dive into the technical and material aspects of this, we have published papers on my lab site, sabinlab.com. But at a high level, we were interested in how building skins could adapt dynamically to their local environments. So imagine a building skin that could dynamically change from translucent to opaque to limit the amount of UV energy entering the building, but also considering how you could dynamically change or create the potential for a window to occur on demand. So we worked side by side in the lab and studio setting, developing sensors and imagers that could learn and adapt locally, and eventually to consider bridging with industry to develop a thin film. And this is the current sort of vision of what this building skin could be. But this project was also super important in terms of embedding a rigorous understanding of structural color, which is highly dependent upon the behavior of light and nanoscale manipulation of geometry and pattern, and in turn, how that interacts with human perception and how we see those dynamically changing conditions. More recently, and building upon the eSkin project, we have embarked upon a unique collaboration with the Defect Lab at Arizona State University to innovate the design and engineering of building integrated photovoltaics, which are known as BIPVs, through the computational design and 3D printing, or through using computational design and 3D printing to create highly customized non-standard filters and panels that result in a site-specific non-mechanical tracking solar collection system. So you're all familiar with photovoltaics. Typically, they're sort of an afterthought stuck onto roofs and buildings with no integrated thought earlier on in the design processes of how they can actually be a part of the design process and engineering process, and importantly, perhaps work more dynamically with their local conditions. So the project is appropriately titled Sustainable Architecture and Aesthetics, Emergent Design for High-Performance Solar Panels, and is funded by the National Academy of Engineering and the Granger Foundation. So we started with biological precedents, looking at biological adaptations, including the heliotropic mechanisms in sunflowers and the light scattering structures in lithopt plants, really amazing specimens, to eventually develop non-conventional configurations of panels for designing with light and energy. And our proposed approach follows solar path data, and in our analysis actually omits the typical 50% of additional structural metal and 30% of copper cable per module. And so, more simply put, we've been able to leverage the benefits of, for example, working with 3D printing to create more non-standard conditions of these panels, as well as looking at part-to-whole relationships and more specifically cellular packing and modular morphology strategies for how we work with these tessellations. So we're currently developing and building a demonstrator pavilion, a prototype that will be sited both in Arizona as well as in Ithaca and upstate New York to collect data and further engage in our analysis. And as a result, the title of the pavilion, Agrivoltaic Pavilion, demonstrates what we believe is one of the first adaptable systems to exhibit extremely low greenhouse gas emissions and therefore showcasing the potential of sustainable design for resilient land use as a model to provide an integrated approach. So this is ongoing work in the lab, and we're continuing to work on this actively. Related to this work, working with structural color, engaging with the design of light and energy dynamically, both in terms of the materials that we work with and the fabrication strategies that we incorporate. In my practice, we've taken these fundamental questions and topics emanating from the research into application. This is a project that recently was completed on Cornell's campus. It's a permanent pavilion structure titled Polyform. It's one of the longest projects that I've been involved with, a labor of love. It kicked off in 2013 and was just completed in 2021. In the project, some of the overarching goals are to engage with humans and participants, and also to consider how this operates within the campus. It was commissioned by the College of Human Ecology, which importantly, their mission integrates design, science, and aspects of human ecology. And so by bridging the nanoscale to the human scale, the hope is that we can leverage emerging technologies and digital fabrication to promote a project that engages active communication across disciplines and across the campus. These are just some of the very early generative diagrams highlighting a series of matrix drawings, exploring how geometry could be active as an organizer, and importantly in how we were beginning to integrate aspects of light and material responsivity. As I mentioned, it's a permanent public installation. It's composed of 4 perforated crystalline metal forms that frames a high-trafficked thoroughfare on Cornell's campus. And the project importantly integrates both environment as well as community through these advancements in emerging technologies to hopefully generate a project that is both responsive but also activates daily routines and exchanges across the college as well as across the university. Just some early models. We did extensive simulation, both with physical modeling as well as through digital simulations to understand the overall responsive effects of the materials and the behavior of light and how that would interact with participants. Just some details of the recent installation and fabrication. And more specifically, structural color is achieved with a dichroic, or what's called a wavelength dependent thin film that's then laminated to the tempered glass panels. And light reflecting from and refracted onto the film changes color and grows warmer or cooler, more opaque or transparent. And this is not based on pigment, but how the film selectively interacts through both interference and reinforcement of certain wavelengths of light at the microscopic scale. So the experience thus generates responses from both the materials and also from the viewers. And really a key component of the project is how we perceive those subtle to dramatic changes of light and color within the material itself. And I'm I'm thrilled to say that it has become a really beloved destination spot on the campus, both for our students, faculty, staff, and outside visitors, which to me really is the moment of success in the project, seeing how people take ownership of it and take advantage of its continually transformative nature as exhibited in the materials and the overall form. More recently, as part of a competition win for the University of Nebraska Medical Center, based in Omaha, Nebraska, we have continued to push the boundaries of what's possible with these responsive materials as a demonstrator, as an active node, again in a campus, this being a medical campus. That also is a part of a network of a series of public art and design interventions, creating sort of waypoints and moments of pause for faculty, staff, and visitors to engage in. I'm not going to go into too much detail on this project, but there were some important leaps that we made with this, both getting into some new developments with robotic 3D printing, which we have been engaged in for multiple years in my lab. I have a large 6-axis robotic arm that we've had for about 8 years now, where we primarily are working with multi-axis 3D printing and specifically with clay, which I'll come to in a moment. But this allowed us an opportunity to leverage that thinking, the tools, the methods, and really push scale and work with a different material, in this case working with stainless steel and specifically wire arc additive manufacturing as a fabrication process, to eventually develop a structure, a spine that would be clothed with a tessellated mesh of dichroic wavelength dependent film to create multiple responses and engagements, both with visitors as well as light itself. We looked into the possibility of setting up a robotic wire arc system in our lab, but quickly realized that we didn't have time within the ambitious schedule of the brief and the project, and this really was an opportunity to create a new collaboration, this time working with Lincoln Electric. They're really at the forefront of wire arc additive manufacturing, working with robots. So here you can see one of their cells. The structural spine for the project is composed of 7 parts that are all 3D printed. Here you can see one of them being printed on the left. So simply you're taking wire arc welding and putting it on a robot and choreographing the toolpath and so on and so forth. Much more involved than that quick summary, but this was a really amazing leap for us and also an incredible collaboration with Lincoln that I look forward to continuing. Here you can see the assembled structure, the main spine of the project. It's been passivated, so the brilliance of the stainless steel is now legible, and you can see through the breaks in the toolpath and the seams how those 7 parts come together. It's approximately 30 feet in height and is the largest 3D printed stainless steel structure in the world, at least at this point. And then the external skin, as I mentioned, is a tessellated polycarbonate surface that is then covered with a dichroic wavelength dependent film. Here you can see some of those details. Here's a view looking through the internal portion of the spine, getting some of those kind of gorgeous views of the 3D printed stainless steel. In the middle, a detail of some of the responses between the brilliance of the stainless steel and the dichroic film, which changes throughout the day and into the night. And also a detail in the middle, you can see the texture, which was just really amazing, that the wire arc additive manufacturing exhibited. And then some views at night in terms of the light scattering onto local buildings within the plaza itself during the day, and a highlight of the sort of playfulness of the structure. It was important to me that this project exhibited a kind of dynamic interplay in terms of equilibrium, so promoting aspects of lightness through the structure and how it sort of hinges on this one moment as it meets the ground with the stainless steel ring meeting the stainless steel robotic printed structure, and then eventually the mesh structure. So this is now open. If you find yourself in Omaha, Nebraska, feel free to take a look. But we were really excited about the successes of this project and how it reached back into the lab and our ongoing work at a deep level with not only robotic 3D printing, but also working through how we translate across scales, working with structural color from the nanoscale all the way to the macroscopic scale in the built environment. The next topic, the second of three, builds upon our ongoing work in adaptive and responsive materials, which bridges, as I've just talked about, between the work of the lab and also the work of the studio, but also takes on aspects of non-standard structures and specifically looking at bricks and part-to-whole relationships, and the question, how might we rethink building materials through 3D printing and biologically informed design. And this work really launched in 2009. At that time, I was still at Penn, and LabStudio was in full force, and we were able to purchase a powder-based printer, which at the time featured the largest build bed on the market. It was a Z Corp printer, which is still in my lab. And from the very beginning, I was interested in leveraging 3D printing technology, not as a representational tool, but as a way of working at a one-to-one scale to rapidly produce parts and components that together in their assembly could maximize and exceed the constraints of the build bed. Related to that, Peter and I were very interested in how we could begin to think about the visualization of data gaining material and how that might contribute to the scientific process. So if one could hold their data, in this case a multicellular structure, how might that allow the scientists to project into their project at hand and therefore hypothesize in novel and different ways. And so we were working on these prototypes, and it was at a key moment during a very hot and humid and sweaty Philadelphia afternoon that I literally realized that I had a body of knowledge in ceramics and clay media that I could bring to an alternative context. So in addition to my graduate degrees in architecture and background in architecture, I also have a BFA in ceramics, and a lifetime ago was a practicing artist in ceramic sculpture and painting. And so this image highlights our first successful 3D printed clay parts. So I took out the proprietary media, mixed up our own high fire stoneware clay media with a little bit of sugar and maltodextrin, all accessible at your local grocery stores, and went from, at that time, this is 2009, a bucket of material that cost $600 to a bucket of material that cost about $1.50. So in USD. So this just absolutely blew me away, that we could 3D print ceramic parts. I wish we had done more publishing at that time, but we were just so in the work and developing the work. And this has since framed a multi-year trajectory. Here you can see the same part on the left printed with the regular media, and on the right printed in our clay recipe. It's been fired, bisque fired, so chemically changed to ceramic, and then glaze fired. So material constraints like shrinkage suddenly become a part of the design suite of parameters that must be considered. This has led to a series of seminars and option studios on the topic of digital ceramics, representing now over a decade of research, innovation, and teaching. And importantly, in my lab, since 2014, 2014, building upon that early work, we've been focusing on bricks. And not only are bricks accessible, everybody knows bricks, it moves across disciplines, industry, and so on. But brick design and the fabrication of bricks really hasn't changed much in many millennia. And so we started with Polybrick 1.0, which you see here, to really work out the constraints, leveraging mortarless connections through age-old means of dovetail joinery. And more recently, working with Polybrick 2.0, we've turned to nature again for a set of design drivers and inspiration, specifically looking at human bone. So why would we look at human bone? First, at all levels, bone is highly adaptive to habitual loading, and this is particularly present within the cancellous trabecular core of the bone. And this also exhibits an anisotropic heterogeneous lattice structure that undergoes adaptive and cyclic processes of regeneration. So through both students' engagement and also core research, we've been able to leverage these key characteristics to optimize for load conditions. So imagine a wall that where the load is the greatest at the base, being quite dense, but then increasingly becoming light and porous at the top. But also to imagine the more phenomenal aspects of a wall that is porous. So here you can get a further detail of that trabecular bone, where we can see how the lattice undergoes constant evolution, guided by its loading condition. So for example, if we were to take a CT scan of the leg of a runner versus a bicyclist versus a swimmer, the density and quality of that bone would be very different based on the history of loading conditions. So we think that's a pretty amazing way, analogically, to think through the design of bricks and the paradox of building with holes. Natural load-bearing structures are characterized by aspects of specialized morphology, lightweight, adaptability, and also regenerative life cycle. And we really aim to apply these characteristics in the pursuit of revitalizing ceramic load-bearing structures. And here you can see some of the details. This was the early stage of Polybrick. You can see on the slides some of the papers that we've developed. Begum Burrell and Yao Lu, who were both graduate students of mine in the Matter Design Computation program, really took this to the next level. And importantly, we've been collaborating with Dr. Christopher Hernandez, who is a mechanical engineer who has expertise in the mechanics of bone. And we're currently going after additional funding sources to hopefully take this to the next level in terms of scale. And more recently, we've been working with robotic fabrication to create one-to-one scale non-standard bricks that exhibit these unique characteristics. We've also undertaken compressive analysis forms, our digital simulations, load path conditions, developing novel methods for bridging, dealing with gravity. As you can imagine, printing porous structures presents a series of hurdles that one needs to surpass. And so we're constantly pushing the boundaries through the development of our own custom software to answer to some of these constraints that we engage with. In other iterations of Polybrick, we work directly with DNA to achieve living glazes to control characteristics such as fluorescence. And this is work with Dr. Dan Lau, who I mentioned in the beginning, who's in biological and environmental engineering. And so in collaboration with his lab, we've been exploring the potential of designing with light and energy through living programmable matter, or what is known as DNA-steered materials. And importantly, this research investigates the possibilities of living building tiles and bricks through the integration of DNA and programmable matter. One of the initial projects that we collaborated on that has informed this current work, also in collaboration with Dan Lau and his team, we explored dynamic DNA material with what's called emergent locomotion behavior, powered by what's called artificial metabolism. So really getting into aspects of life and living matter. And this work is documented in a recent paper that was featured on the cover of Science Robotics, where we're looking at the promise of how metabolism is a key process that makes life alive. And the combination of anabolism and catabolism sustains life by a continuous flux of matter and energy. So in other words, the materials comprising life are synthesized, assembled, dissipated, and decomposed autonomously in a controlled, hierarchical manner using biological processes. And this paper is available on the lab site if you're interested in taking a deeper dive into that. And so we really leveraged the success of that work to then integrate with our ongoing work with 3D printed clay and ceramics to develop Polybrick 3.0, and we had to go back down in scale. You can see here these little discs, which are the size of approximately a quarter, and have actually recently been able to work at scale, which you can see here in polytile, which is super exciting. So this specifically is a 3D printed 5-inch by 5-inch porcelain tile, where we're designing the microscale texturing, as you can see in this detail, to interact with a substrate of DNA hydrogel. And that allows us to basically create a switch between how these fluoresce. So at the kind of first phase, we're controlling the emission of light or fluorescence. So these tiles, in summaries, utilize novel patterning techniques and hydrogel biomaterials to tune surface conditions at both the micro and macro scale. Our next phase is to not only control the emission of light or fluorescence, but also to look at the promise of how these DNA hydrogels can interact locally with their environments. So imagine a wall that could glow and therefore alert you to contaminants that are in the air. So the next phase is to consider how a building wall that's tiled with these polybricks can actually serve as a signal. And then the third phase is to consider how these DNA materials could also locally clean the air of particulate matter. And that can be done by controlling the DNA sequence, but also the proteins that the DNA interact with. And then lastly, in this series, another really successful example, which exhibits the same characteristics and also the same methods. This is a 1-to-1 scale tile, where in this case we have gone back to some of the earlier topics that we've explored, including superhydrophobic and superhydrophilic materials, so materials that repel or absorb water, and how that can be controlled through the fine-tuning of geometry and patterning. And so here you can see how we're controlling the direction of water, so that this is an image of the same tile now in a vertical orientation. So those little dimples are holding the water and controlling how it's moving across the tile itself. So imagine a tiled wall where you could passively cool a local building element or condition, or perhaps control the direction and flow of water to, say, for example, design a green wall more effectively. So you can see, again, some of the details and responses and successes that we're getting with that. And in conclusion, I have a video that summarizes this work just to give you a kind of behind the scenes, deeper look into the various phases that we've been exploring. And as I mentioned, we're now currently going after a couple of grants to hopefully take this to the next level in terms of scale and really beginning to look at the promise of how these polybricks can operate in architecture. The production of ceramic blocks and tiles has a long technological and design history. Ceramic modules of standard measurement have been used as building block and replacement of stone for many centuries. Ceramic bricks and tiles, so ubiquitous in their application in the built environment, have surprisingly lacked recognition as a viable building component in contemporary architecture practice until now. Polybrick, our latest endeavor under the topic of digital ceramics in the Sabin Design Lab at Cornell University, showcases next steps in the integration of complex phenomena. This work includes advances in digital technology, 3D printing, advanced geometry, and material practices in arts, crafts, and design disciplines. The first phase of the Polybrick series features the use of algorithmic design techniques for the digital fabrication and production of non-standard ceramic brick components for the mortarless assembly and installation of the first fully 3D printed and fired ceramic brick componentry. Polybrick 2.0 is generated with the rules, principles, and behavior of human bone formation. This allows for the production of variegated bricks that are light and porous at the top of the wall and dense at the base to carry load and maintain efficient structural integrity, while also amplifying material and formal expressions. Polybrick 3.0 takes our material investigations to the next level. Synthetically designed with advanced bioengineering, these biobricks will exemplify the cutting edge and future of biologically steered clay and ceramic building blocks in architecture. The two prototypes utilize 3D printed clay, hydrogel, and synthetic DNA. As you can see here, a unique ID stamped with DNA in the form of a C for Cornell is fluorescing within the polybrick clay body. Brick stamping has a long history where variegated size, shape, and stamping indicate place, date of construction, and type, and thus serve as invaluable historical documents. With our unique DNA stamps and glaze, we explore the possibility of live signatures and dynamic surface techniques, coupled with non-standard bricks in the context of living matter and digital ceramics. So I invite all of you to take a look at some of our published papers on that body of work if you're interested in taking a deeper dive, and definitely watch our spaces as this work is ongoing and hopefully will extend well into the future. So this brings me to my last topic of the three, and of course there are many overlaps and connections between these various projects and research endeavors. This last topic really starts to touch upon that third phase that I talked about at the beginning, where we're able to push some of the successful prototypes into the built environment and really begin to test and consider large urban interventions and diverse publics and communities that engage with the projects. And also to consider the question, how might we design and enhance architecture with the bioarchitecture and behavior of our own bodies and local environments, as well as the connected question, can building materials be made more responsive through their integration of artificial intelligence and big data. This is also where I have taken a deep dive into the possibilities of textile processes and fabrication. I've spent a number of years working with weaving and also specifically digital knitting processes, collaborating with industry partners such as Shimashiki, who are at the forefront of what's called whole garment knitting. They not only make the machines, but they also do production. So the kind of big idea there is seamless 3D knitting. And at the time of this project, I won't talk about this in detail, but this is the MyThread Pavilion commissioned by Nike and completed in 2012. Shimashiki, my now multi-year collaborator, they had primarily only worked at the body scale and extensively working with fashion designers and clothing design and production. And working together, we were able to really push the possibilities with both scale, but also the possibilities of working with these incredibly complex knit geometries and materials. And this specific project for MyThread, or for Nike, titled the MyThread Pavilion, was an opportunity to integrate my ongoing work within structural color, for example, and importantly, the integration of the dynamics of light and energy and how that can be applied to generate spaces and forms and overall organizations that are highly transformative and immersive. So this was the first time that I started to work with high-tech responsive fibers, including photoluminescent, as well as solar active fibers, which directly interact with the sun or a UV source to collect UV energy and then release it, or to dynamically change color in the presence of changing UV. I will mention that in this project, Nike was about to launch their new technology and material now known as the Flyknit, which is, I'm sure, familiar to all of you. And I proposed to them the development of an experimental pavilion that would integrate both the processes of knitting, but also a series of dynamic biodata sets, which came forth through a series of workshops, not as a representation, but to really consider the hidden structures and dynamics of that data as a set of design drivers that were directly linked to the parameters of knitting and digital production. Textile fabrication also, serves as an incredible bridge in terms of my ongoing work in integrating biosynthetic processes. My interest in turning to nature and biology has never been about simply translating what might be a tantalizingly beautiful form in nature into an architectural or formal possibility, but really to probe what's behind those images, to take a deep and rigorous dive into the processes of surface design, for example, in biological systems, which is something I spent 8 years on working with Peter and his expertise in this area, to understand how morphologies change and bifurcate, how hierarchy is exhibited across scales, and to bring that back into our own design thinking as an analog. And these are some images from a project for the Cooper Hewitt Museum as part of their 5th design triennial titled Beauty. And in this project, it was the first time I began to work with Arup Engineering, and specifically Clayton Binkley, who is no longer with Arup, has his own practice, and is continually involved with my work. And this enabled us to take a deep dive into how we were integrating stress strain and the performance of the knit geometry. There were no tools off the shelf that we could work with. We had to develop everything from scratch. And so we produced a series of swatches to understand at a deep level the parameters of the knit and how that would inform at a global scale the performance of the overall project, in this case, the pavilion for the Cooper Hewitt. So specifically in this example, by instantiating more holes into the knit material, you intuitively would think that that would create a stretchier fabric, but actually it does the opposite. It stiffens the fabric because essentially you're creating a bunch of knots. So we were able to leverage those findings and begin to design with them dynamically. And this was also the first time that I started to work with a double surface, where in this case the cones, the digitally knit cones, behave as springs, which I'll come back to in a moment. And then the largest instantiation of this work is certainly Lumen, the winning competition entry for MoMA and MoMA PS1's Young Architects program. We were fortunate to win this prestigious prize in 2017. The AAP program is no longer happening. It's, I think, temporarily on pause, but really incredible experience. I'm still recovering from it. Incredibly fast project, big project. But I knew if we were going to win, we needed to work with a material system that already had years of R&D development and really was at the point where it was ready to be taken to a public context and to an altogether much larger scale. And so we were able to take all of this work, both coming from the fundamental research in the lab, as well as through the pavilion projects, which I really see as sort of prototypes, demonstrators of how to push the research into application, and to grapple with a much more complex site. So I was interested in how we could work with the existing matrix of courtyards actively. So the canopy structures stitch into the existing matrix of concrete walls in the MoMA PS1 courtyards in Long Island City. This was also an opportunity to work directly with the environment and the sun, to think about how the photoluminescent responsive fibers would transform and absorb UV energy throughout the day and then emit light at night. And there was a kind of sweet spot moment right at sunset where all of the fibers just would slowly start to release what had been collected throughout the day into this incredible glow. And here you can see a highlight of that, which was then amplified through the latter hours of the evening with a lighting treatment. We had to think very creatively through what was a very minimal budget, taking advantage of off-the-shelf materials. Here you can see a detail of how the canopies stitch into the existing walls. We also had to consider elements of shade and water as part of the brief, and so the large canopy structure exhibited a interactive misting system that was incorporated into the webbing network at the top, and then connections through the tubes would go down into the digitally knit cones and served as a dual purpose, one to tension the cones, but then there were nozzles within each of those rings that would then gently mist visitors below. And so with the integration of a few IR sensors, infrared sensors, we were able to create a very kind of dynamic condition, and it basically just would shift the pressure differential in the system by flipping the solenoid valves, which created spatially and acoustically a pretty amazing experience, and functioned quite well in cooling the local microenvironment below the canopy. Here's some images at night. The entire project was designed to be active and dynamic and responsive, both in terms of its structure, but also in terms of the responsivity of the materials. There are 3 tower structures. All of them are tensegrity. Here you can see a detail of the flying ring and the ropes that generate a diagrid to work with both the central mast and the platform below, which added a kind of third envelope of equilibrium to the project. It was engineered to take live loads, but people were not supposed to climb the towers, but they certainly did. And the Saturday warm-up sessions, which brought DJs and performances and artists from around the world, brought in upwards of 7,000 people during each event. And I found these events quite harrowing, but the project held up really well, and this, I think, image in our current context within the pandemic is really powerful, and I sincerely hope that we are able to gather in this way in the not so distant future. But for me, the success of the project was witnessing how people took ownership of it and made it their project. And I received so many comments from visitors who said they frequented it during the week to take their lunch. They wished that it was something that was at their child's playground. One person said that they thought this type of architecture should be in hospitals. So there's something to the unique kind of informal nature of both the material, how it's structured, its geometry, that begins to erase sort of borders and boundaries, create a more flexible and open and informal attention-holding architecture, as Jenny Odell talks about, that I'm deeply interested in, that moves from the kind of fine-scale, rigorous, deep dive into the systems of biology and bringing that to the public and sort of diversity of urban conditions and diverse publics. I'm now getting to over time, but I'm going to conclude with this last project. I'll go through it fairly briefly, but this was also a really important project which builds upon the previous work that I just presented, and is a project titled ADA, and was a part of a commission and also opportunity that I had working with Microsoft through their Artists in Residence program between 2018 and 2019, which was just an absolute incredible experience, being able to work directly with teams at Microsoft Research, where they're engaged in core research. They have longer sort of stints of time to explore topics, and Microsoft Research within their Redmond campus, their home campus, there are a number of teams working on AI. So in conjunction with this work, we've been exploring how artificial intelligence can personalize rooms and buildings. And so, for example, the spaces and environments that people inhabit influence how we feel, and also, therefore, how we act. And so through the course of this project, working with researchers and engineers at Microsoft Research, this prototype, ADA, is driven by individual and collective sentiment data that's collected and housed within their building, which is called Building 99. This diagram just highlights some of the kind of technical details and material systems that we worked with. We worked with a network of 3D printed nylon nodes. So you can see some of the things that we built upon from previous projects. So this also exhibits a double skin, but a much more refined, equal and opposite choreography of forces. So the external skin is a semi-rigid exoskeleton composed of these 3D printed nodes and fiberglass rods, which runs concurrently with the tensioned netting of the interior surface. The lighting system and materials of the cyber-physical architecture respond to human participation as individual and collective facial pattern data. And so through a network of cameras, we're collecting facial pattern data that's then processed by AI algorithms and transmitted as sentiment through light and color. So this highlights the pipeline of how that works. And so the end result is reflected back into the pavilion as a change in material response and a change in color. So a really key component to this and aim of the project is to expand and inspire engagement with humans through architecture as an interface, and also importantly to open up conversations around the use of AI, hopefully kind of opening up more of the kind of dystopic topics into trajectories that could be more human-centered, giving agency back to humans, understanding how data is power, and personal data is power, and how do we create opportunities for generating agency. And so while artificial intelligence powers the project through the precise narrowing and statistical averaging of data collected from individual and collective facial patterns and voice tones, the architecture of Ada augments emotion through aesthetic experience, and thereby hopefully opens the range of possible human emotional engagement. And in turn, importantly, the project also opens new pathways for fundamental research at Microsoft Research. So they're using this as a platform. The software pipeline is purposefully flexible. The architecture of it is flexible, so it can take any type of data. So they're using this as an interface to explore aspects of data that otherwise might not be discernible. Here you can see some images of the first night that it was open, and this group has just suddenly realized that by smiling together they can elicit a response. So inside there's a central camera that overrides all of the other cameras throughout the building. So here they're actually driving and steering the project. So personalized architecture, in this case, may sense subtle changes in human emotion, and in this case through sensors and interfaces that detect changes in facial patterns and voice tones, which is a large part of my collaborator's research, Daniel McDuff. He led the team that I worked with at Microsoft. And hopefully respond in ways that increase well-being and promote healthier environments. So with that, I think I will conclude. There's a really great, maybe I'll play the video in the background as we move into some questions. But I really see this project again as an experimental demonstrator, and sort of looking at the potentials for where we may go through the use of these technologies. And so while Ada offers subtle and abstract interactions with humans through space, material, and form to augment and expand our emotional range in a specific context, in this case an office environment, this in turn affects the probable sentiment data being collected as new information. Because the spaces and environments that we inhabit influence and partially shape who we are and how we are feeling. And the hope is that through the integration of responsive materials and emerging technologies, Ada can offer an interface for personalizing architecture to make it more human and reflexive, and hopefully expand the potential of human emotional engagement through both materiality and beauty. And hopefully at the same time to open questions around the potential of architecture to influence aspects of healthiness and well-being through the direct engagement with the spaces and forms that we inhabit on a daily basis. So with that, I thank you for your attention, and I'll play this video in the background, and I look forward to your questions and to a discussion with you, Wolf.
Great. Thank you very much, Jenny, for this fantastic, and I would agree, very beautiful body of work that comes out of your research. And yeah, at this point, I'm very happy to invite Wolf Mangelsdorf to the stage, and happy to give over the screen to the two of you.
Thank you. Thank you, Maya. And yeah, Jenny, fantastic. This was really inspiring, right? Because it sort of speaks to one of the core issues that I see at the moment. And that is, you brought it up at the beginning. Yeah, we have all the challenges around the polluting aspects of our work, yeah, the embodied carbon in particular, the footprint that leaves behind, and the the responses that I see in the professional community that I'm involved with so much is always having a tendency to go towards what in German we would call bieder. Yeah, I can't find an English word for it. It's at the same time modest and boring. And your work is neither modest nor boring. And I found put a massive smile in my face because it is actually expressing through its playfulness a kind of optimism of how we can go about these issues, right? And yeah, so it's not really a question and nothing you can respond to really. It's just I needed to get that off my chest. I found that really inspiring. But if you dig a little bit deeper into it, I have a few questions around how we now take this, or how you take this to the next level, because I don't know if you have similar observations around how we as an industry are reacting to the challenges. That do you perceive this kind of boring modesty that I was there, the Biederkeit that I was referring to?
You mean in terms of next steps and really pushing?
What I'm trying to say is how do we react to the material challenges, to the ecological challenges, and so on, without retracting ourselves into we're doing nothing anymore, or like we're shell shocked, or we make everything out of massive kind of timber logs or something. Yeah, yeah. Do you perceive something similar, or is that something that you I don't know. Yeah.
Yeah, no, it's a really great question, Wolf. I think it's a complex question to answer, and part of that is that we don't have the answers, and what we need are new models, and that means at all levels and multiple aspects of our profession and discipline, which include pedagogy, and how we teach. We still incorporate, at least in most schools, a Beaux-Arts model that has a very strong hierarchy and at its core, a kind of value system that promotes the architect as a kind of sole actor and author. And we really need to not only break that down, but to encourage early on in our teaching and the development of pedagogical structures, collaborative models for working across disciplines, and that's going to take work, because at the end of the day, it's really difficult to collaborate. We operate in disciplinary silos, and it's important to have disciplinary expertise as a T, to have that expertise. But figuring out.
No, I'm just saying, sorry to interrupt you, but I'm grappling a little bit with the transdisciplinary aspects. Yeah, this is a big one for us. And I come from the background of a multidisciplinary engineering firm, and yeah, for us, it's all about transdisciplinary or transdisciplinary collaboration. But without somebody taking the design lead, it also leads to failure. I've seen this also converge to the lowest common denominator, and again become extremely boring. So finding that, and I think we can see in your work that it isn't without like a strong hand guiding it in the background. Yeah, it all carries your handwriting, and I think that's absolutely beautiful. So finding this balance, this equilibrium of the true collaboration that allows all the different multi and interdisciplinary or transdisciplinary aspects to come to the fore and actually become much better in the end, but with strong, let's say, design leadership. Yeah, I don't know if you see that similarly.
Yeah, no, I completely agree, and that's where our expertise as designers, and our training, our ability to think comprehensively and effectively through a complex array of constraints and questions, to synthesize that, formulate a plan for action, and to really be a leader, is really critical. But we constantly devalue what we have to offer, right? And I think
as designers, you think?
Yeah,
okay.
I think so. And pushing ourselves into into other spaces that may be uncomfortable, such as, working with biologists or working with computer scientists, etc., I think really is the answer to addressing some of these larger questions and crises that are on at the forefront, because we can't do it we can't do it alone. And so my point was that about pedagogy is developing models that encourage that earlier on.
Mm. No, I agree with you, and it's not always going to be simple, right? Because I think the patterns that we see in the world that you described, yeah, the sort of Beaux-Arts model that they translate themselves still, I think, into pedagogy, yeah. Mm-hmm. And it's rare that you see the true kind of transdisciplinary collaboration happening.
Yeah, I think the other thing too is integrating more research with practice and vice versa, and establishing structures and models for doing that. I mean, I think we're at a really exciting moment where, a lot of my colleagues and friends who have been pioneering this work, the space of our production for many years was in the gallery and the museum, because that's that's where we got support. And now you're seeing some of those same people really pushing boundaries in terms of how the work is actually reaching the built environment and being built. But there's so many hurdles to move through, both in terms of getting contractors on board that are willing to take risks and develop new strategies for working with these types of materials, litigious issues that come up with materials that are not, they don't even have a code structure in place for materials like eSkin, so there's, I think, many constraints in the works that require.
You're touching on a really interesting subject that I've been sort of observing over the past, God knows, almost 20 years now, right? That traditionally the architects or the designers are those who design, and then the builders come in and they build what the designers have designed. And increasingly, those who are the builders are fading into the background. And the studies that you've done and that others in similar areas are doing too are very much involving the whole construction methodology, the production side of things. I almost get the feeling that it works in reverse in your case. Yeah, your fascination with the production methodology, be that the clay or be that the 3D printing of the stainless steel or the 3D knitting, yeah, is informing what you do with your design. And I think that's there's even a further decoupling, I think, is happening somehow from what's happening in 3D printing. If you look at what's going on in academia and in what you're doing there, and what's happening in the construction industry, yeah, it feels like the construction industry is limping about 10 years behind, yeah, and funny, isn't it? Yeah, that somehow there's this new merging of design and manufacture, and at the same time a decoupling from what's happening in the construction industry.
Yeah, no, completely. But I'm encouraged by some of the things that are changing. So, for example, the NSF here in the States recently launched a new program that's titled Advanced Manufacturing. Mm-hmm. They're very invested in the questions and topics that you just raised, and I think some of the more successful models, such as construction dynamics here in upstate, or construction robotics, or Boston Valley Terracotta, basically what they're doing is, they're not getting rid of their longtime employees who have years of expertise in masonry systems, for example, but instead bringing on recent graduates who have expertise in robotic fabrication, etc., and bringing the two together to upskill and learn and really push what's possible. And those, I think, hybrid models are really encouraging in terms of closing that gap.
Yeah,
but,
yeah. Go
I
on.
was just going to say, Mario has written about this paradigm shift extensively, for sure. You know, we're seeing a huge paradigm shift that hasn't, you know, hasn't occurred for many, 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 many years, where architects now are in the position to design and make and fabricate in real time. And as you
Yes.
say, consider the construction and material production as an integrated part of the design process, which shakes up the kind of hierarchies and roles of how buildings are built in a kind of interesting way.
And in many ways, I think we need that, right? If we go back to those numbers that you gave us at the beginning, yeah, those numbers that we're becoming increasingly familiar with, the 40% emissions coming from buildings, and out of that, yeah, 11 or 12% coming from just purely construction. Yeah, the fact that we are having so much embodied energy or embodied carbon in the materials that we're using and the processes that we are deploying. I think it's highly necessary that we embark, we as designers, we as those who are looking at these issues and how we design our way out of them, basically, that we look at the material strategies, because I see sort of numbers here and there, yeah, that kind of assume that we get to zero or embodied carbon by 2050, just because nobody will do carbon capture and storage and still produce cement. I don't think that's the way forward, right? So there need to be more intelligent methodologies that have to do with how we deploy material, how we develop it, and so on. And how much are you connected to I don't know, those you just mentioned, yeah, that turn this then into something that is deployable on a much bigger level?
Yeah, I think we're close with the Polybrick work in terms of engaging an industry partner and rethinking, you know, how bricks are constructed and how construction assembly happens on site. I mean, imagine a fleet of 3D printers that are on site working with local clay matter. You know, so there not only sustainable approaches to the use of material, but efficiencies gained through the process itself. And we're already seeing that with 3D printing, robotic 3D printing in concrete, you know, that it not only is less time consuming, but you can save vast amount of material and therefore limit waste that goes back into landfills and contributes to these horrific percentages that we're all familiar with. But again, I think that what we need are stronger collaborations between those that are kind of really pushing boundaries in research and those that are engaged in the construction of buildings and working together to close that gap.
Just so something that crossed my mind when I looked at that 3D printed bone structure type brick. Do they have insulation or insulating properties? Yeah, because they trap so much air. If you were to kind of just cover them on either side with something that is a surface, have you tested that? Or I'm going a little off.
No, great.
It's just something that I found really interesting, right? That you have multiple purposes out of one material, maybe.
Yeah, it's a great question, and it is something that is a part of the current trajectory of the research, and actually informed a recent grant proposal that Dan and I and others that we recently completed, considering how we could work with the DNA hydrogel as an insulating material. I mean, Dan's work is just mind-blowing. They've recently developed a strategy for creating these macro scale thin films that have, you know, thermal properties and potential to be integrated to answer to some of the questions that you just brought up. So we haven't achieved it yet, no, but it's definitely
no, it's just something that crossed my mind. Yeah, I mean, I saw it. Yeah, I want to bring it back to sort of what you landed on somehow. Yeah, this kind of interaction, the agency that the individuals have, and so on. And maybe start with with something that's important to me and a bit of a statement almost. Yeah, I do think the most important thing is that we build for humans and that we are actually creating environments that are livable. And if we miss that bit, then the whole kind of sustainability drive is just a lost cause in a way. Yeah, because now I wanted to come back to the most fascinating of them all was actually Lumen. I found, yeah. So this picture with like the place rampacked with people and so on. Is this something that you will bring back on some grander scale? Yeah, if it's Microsoft, it's sort of hidden there, maybe kind of accessible to 2 or 3 people. But I'd love to have one of those in my playground or backyard as well. Yeah.
Yeah, no, definitely. And we've been fortunate due to the success of Lumen in my practice to receive a number of commissions for permanent projects.
Oh, brilliant.
I didn't talk about the newer projects this evening, but one project we recently finished in Abu Dhabi, which is a public beach intervention project that's permanent. And public space in the UAE is not something that's at a premium. So having this be part of Abu Dhabi's as a city, their mission to generate more public space is really exciting. And we're working on a project in San Diego, in Louisiana. So we have a number of things in the works currently that definitely build upon the success of Lumen and how it attracted people and really operated in I think a transformative way. And that's yeah, it's exciting.
This 3D knitted or this knitted material that you're using there, what kind of material is that? Is that a nylon material?
Yeah, so the fibers themselves are synthetic, which is important. Like we couldn't work with organic cotton or wool.
No.
It would be impossible. And more recently, so for example, the project in Abu Dhabi, I collaborated with Gore to develop a PTFE photoluminescent material. And any canvas structure that you see in an extreme environment like the UAE or California, etc., typically is going to be made with PTFEs. So that was a really informative and exciting period of time to work with them on that. So we're continuing to push that in other projects that are outside and have to negotiate the extremes of the elements.
And Sliver hopes, since this is the last lecture of our winter term, but we will continue in the summer, so Sliver hopes to maybe see you back in the audience at some points when we continue discussing for the next term research and design and its relation to architecture. Thank you, everybody, and
Thank you.
Yeah, thank you. Take care, everyone. Stay safe.
Bye-bye. Stay safe.
Bye.